Oftentimes when we count things, we have to be careful that we don't accidentally double count. And so this is where it's important to understand a little bit of lingo with regards to how we count things. And we can either count things that are parts of what we call disjoint sets, or we can count things that are part of non-disjoint sets, or joint sets, I guess you could call them. Now let's imagine that we're counting something, and we'll just focus on really two sets. And if the sets have nothing in common, then we would call them disjoint. And that also implies that there's nothing inside of their intersection. In other words, the intersection is empty. And so we would signify that with an empty set. For instance, the set A could have, three elements like 1, 2, 3, and maybe set B has elements 4, 5, 6, and 7. Well, if I want to count the number of elements inside of A union B, remember A union B means take all the things from A, all the things from B, and put them together. And how many things would you have? Well, you'd have 7, right? Because you have 3 here. We have basically 3 plus 4, right? And so in this case, notice that it's adding the number of elements in A plus the number of elements in B. Remember, we use absolute value for that. That's just absolute value means how many, the quantity, the magnitude. And so other times we may have a non-empty overlap. And let's see what happens there. Well, let's suppose that A by itself has elements 1 and 2. B by itself has elements, we'll say, 5, 6, and 7. And in common, they have elements 3 and 4. So basically, A has 4 elements, B has 4 elements, but they have 2 in common. So the problem with saying that the number of elements collectively in both sets, if we gathered them together and counted how many elements we had, if we just said that this is the number of elements in A plus the number of elements in B, well, then we'd be saying that there are 4 elements in, and I'm sorry, I think I maybe said 4 elements in B, but there's actually 5 elements inside of B, right? 1, 2, 3, 4, 5. If we added those together, we'd see that we get 9. But we can see that there are only 7 numbers. So what's happened? Well, the problem is that the number of elements in A, if you add those together, let me just go ahead and highlight them. That's going to be these guys, right? 1, 2, 3, and 4. So we're counting those 4 elements as being part of A. You might see where this is going already. Now inside of B, we're adding 1, 2, 3, 4, 5. And if you notice, we've counted 3 and 4 again. We've counted it twice because being part of the intersection still means it's part of each set individually. So if we essentially double counted the 3 and the 4, right? We really wanted 7 elements. We counted 9, but we counted 2 too many. And so as a result of that, the way we can easily deal with this problem is, well, one way is just to add up the components individually, that are just in A, just in B, and that are in just A and B. Although that can become kind of tedious for larger sets to deal with that many individual segments. So what we can do is we can say, well, since we're double counting the number of elements in the intersection, we can just subtract that off. So this is the double count. We're remove 1, double count, and so if you subtract off 2, well, in that case you get 7, and that's exactly the number of elements that are there. So that's how we often deal with non-disjoint sets where there is an overlap. And so in general, I like to just say, if you focus on the sum of the total number of elements between A and B as the number in A plus the number of B minus the number in both, you'll pretty much never go wrong with this. Because in some cases, like in the first example, if we applied this exact same formula of it's the number in A plus the number in B minus the number in A and B, well, the way that would look, it would be 3 plus 4, but then there's nothing in common, right? The intersection is empty, so it would just be minus 0, and that would still give us the 7 that we got up here. So in some cases, if the intersection is empty, then you're just subtracting 0, but it's important to be mindful of that. Is there an intersection? Subtract it off, even if it's 0. All right, well, the way this comes in handy, we know we can apply a multiplication principle, and sometimes we add things if we're just trying to total things up, but when we're grouping, a lot of times we multiply because we want to count the number of sequences that we can generate out of a finite number of things. So let's consider the word math. We want to know how many 2-letter or 3-letter words can be created from the letters in the word math. Well, that's two different things, right? We can think about the 2-letter words. We could think about that as maybe set A, and we can think about the 3-letter words as set B. And we have to ask ourselves now, okay, how many elements would be in the intersection, right? We need to count the number of 2-letter words. We need to count the number of 3-letter words, and then subtract away any words that that those two sets have in common. Well, if we think about what this would look like, you can't, if you collect all of the 2-letter words, well, those are words that have 2 letters, right? So, for example, M-A, M-T, lots of different possibilities here where we grab 2 letters. But then B there's no overlap between A and B because these are going to be M-A-T, M-A-H, right? 3 letters. Now don't get thrown off by the fact that some of these are also found in these. 2-letter words and 3-letter words are different. If you've done any coding, then you know that if you define a variable as M-A, and then you define another variable as M-A-T, those are not the same. Those are distinct, even though they contain some of the same letters. So there's not going to be any overlap. So in order to find the number of elements that are 2-letter or 3-letter words, we're going to add up the number of 2-letter words plus the number of 3-letter words. And still, we'll put this here as subtract away the number of words that are both 2 and 3-letter. So these are 2 and 3-letter. Impossible, right? So this is actually going to equal 0. Well, how do we get the number of 2-letter words? Well, remember, we're grouping one letter with another letter, and the fact that we're counting the number of groupings, the number of pairs of 2 letters derived from the word math, means that we're going to multiply. So imagine why we're going to have first letter could be M, A, T, or H. And then if the first letter was M, then for a 2-letter word, the second letter could be A, T, or H. If the first letter was A, it could be an M, T, H, T, M, A, H. So T, M, T, A, T, H. And then if the first letter was an H, you could have T. I don't know why I'm doing this out of order, but you get the idea here. And now you can see that this 4 times 3. 4 times 3 equals 12 2-letter words. And that's also, if you wanted to use a permutation, right? Then you could say from 4 letters, I'm going to draw 2. I do want to consider MA and AM as being different, so this would also give me 12. Multiplication principle, a lot of times is easier. In my mind, sometimes it distracts us from the actual counting that's taking place. But if we do remember that all this does is 4 times 3, that it multiplies a descending set of integers from the starting integer down to 1 or something above 1, then permutation formula can be handy. Now, if we do the same thing for 3-letter words, the only difference is going to be there will be 4 possibilities for the first letter, only 3 for the second, and then because we've used up 2 letters, there are only 2 letters remaining. So there would be 4 times 3 is 12, times 2 is 24 3-letter words. And again, you could do permutation 4, 3, so that would also give you 24. And now what do? Well, you want to count the number of words that are 2 letters or 3 letters, so now we can say this is going to be 12 plus 24, which equals 36. Very nice, very nice. So that's how the idea of disjoint, non-disjoint applies to counting groupings of multiple things, or multiple groupings of things. Let's get one more non-disjoint, then we'll look at a disjoint set, and then we'll look at a non-disjoint one. Suppose we have a program that allows variable names to be 1, 2, or 3 letters in length. Well, again, notice that in this case, you can't have a variable that's going to be both or all 3 of these things, 1 letter, and 2 letters and 3 letters. So these are going to be, again, disjoint sets. In this case, we have 3 of them, right? We can think about the 1-letter variables as set A, or whatever we want to call it. This as set B, and this as set C, the number of 3-letter words. Now, in this case, if you had 3 Venn diagrams, it gets a little trickier because if they are non-disjoint, then that means that there could be some weird overlaps, and you'd have to actually subtract off a couple of things and add one more thing back. We're not going to get into that because these are again disjoint. You can't have a variable that is simultaneously, say, 2 letters long and that is simultaneously 3 letters long. So, okay, let's count the number of elements that are in A. And we can only use lowercase letters and the digits 0 through 9. And you can't have a digit in the first position of the variable name. So, okay, well, that means that for the number of 1-letter variables that I can create, it's only 1 position, and that's the first position. So the first position can't be a digit, so that means you can only select one of the 26 alphabetical letters. Set B, the number of 2 letters, well, once again, you can have 26 possibilities for that first quantity, any letter. But then for the second digit, and we are grouping here, we're pairing two characters together. I shouldn't have said 2 letters, 2 characters together. The first has to be a letter. The second one can be any of the 26 letters as well as any of the digits, and there's 10 of them, so this would be times 36. Set C, similar. For the first character, you can have 26 letters, one of 26 letters. Then you can have any number or letter, and then you can have any number or letter. It doesn't say we can't repeat them, right? So we could repeat the same. It could just be AAA as a valid variable name. If we couldn't repeat them, then we'd have to decrease the number of elements each time, 26 to 35 to 34, right? Because that would mean that you're removing those 2 things that you've already drawn. And then we would add these together. So I'm just going to write it like this. The number of elements, in this case, that's 1 letter, or 1 character, 2 character, or 3 character, is the number of elements that are 1, plus the number of elements that are 2, plus the number of elements that are 3 characters in length. And I'll just write it like this. You can do the calculation. And then 26 times 36 squared. Awesome. Now let's look at a non-disjoint situation. How many integers between 1 and 50 are multiples of 3 or multiples of 4? We look at the picture of this and we think about numbers that are multiples of 3, and then we look at numbers that are multiples of 4. Well, there are some numbers that are multiples of both 3 and 4. For example, the number 12, 3 times 4, right? That's a multiple, that's 4 multiples of 3, and it's 3 multiples of 4. So here in this case, A and B have an overlap, right? It's going to have some overlap. For example, 12 is going to be in here because it is a multiple of both 4 and 3. And if we start to list these out, this is probably my favorite way to approach this, is list out the elements in A. There's not that many of them. Starting at 1, so 1, oh, 3, I'm sorry, 1 is not a multiple of 3 though. It has to be a multiple of 3. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33. I can make it. 36, 39. Nope, 42, 45, and 48. So those are all the multiples of 3. Multiples of 4, there's fewer of them. Starting with 4, 8, 12. All right, check it out. We already see one in common. 16, that one's not in common. 20 is not in common. 24, yep, 24. Lo and behold. 28, nope. 32 is not in common. 36, that's in common. 40, 44, and 48. 48 is in common as well. So in this case, we'd have to say that the number of numbers that are multiples of 3 or 4 is the number of multiples of 3, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's 16 elements, plus the number of numbers that are multiples of 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Minus the number of elements that are both multiples of 3 and multiples of 4, which would be 1, 2, 3, 4. There are 4 numbers that both sets have, and those are therefore being double counted both in A and in B, so we have to subtract it off once. This gives us a total of 24. So this is how we use disjoint, non-disjoint counting when we're, even when we're grouping. So we learned that we could count the number of groupings, and now we realize that sometimes we need to count the number of groupings multiple times, like 1, 2, or 3 character variables, or where we have numbers that are multiples of 3 or multiples of 4.